Hello everyone, welcome back to my Wonder Channel. Today, we're diving headfirst into a mind-bending world where the everyday rules of life can be twisted, and where everything seems to happen all at once. Get ready for a quantum-level brain workout. Sounds like something straight out of a sci-fi movie, right? Well, guess what? It's not magic, it's real science. Welcome to the incredible world of quantum computing. This is a place where supercomputers aren't just powerful machines. They're like digital wizards that can solve mind-bogglingly complex problems at lightning speed. It's a world where the usual rules seem to go out the window. Imagine this. You have a coin. With a classical computer, that coin can only be heads or tails. But in the quantum world, that coin can be both heads and tails at the same time. Yes, you heard that right? That's the magic of the qubit, the fundamental unit of quantum computing. This mind-blowing phenomenon is called superposition, and it's just one small trick in the massive magic show of the quantum universe. But hold up, there's more. The quantum world also has another spell called quantum entanglement. When two or more qubits become entangled, they're so tightly connected that even if they're thousands of kilometers apart, a change in one qubit will instantly affect the other. In simpler terms, it's like you and your best friend being able to read each other's minds, even if you're on opposite sides of the planet. Thanks to these extraordinary abilities, quantum computers can perform millions of calculations simultaneously, while classical computers are stuck doing one step at a time. To put it into perspective, a classical computer is like cooking one dish at a time. Only when one is done can you start the next. Meanwhile, a quantum computer is like whipping up an entire feast all at once, or in the blink of an eye. Wow. If your brain feels a bit quantum tangled right now, don't worry, you're not alone. In today's video, my Wonder will take you on a fun and easy-to-understand journey into this mysterious quantum world. We'll break down the complexities of quantum computing with a pinch of humor and a dash of simplicity. Our mission is that by the end of this video, you'll walk away with a smile on your face and just enough quantum knowledge to casually flex to your friends. Hey, do you know what a qubit is? And don't forget, hit that subscribe button so you won't miss any of the exciting and mind-blowing content coming up on my Wonder Channel. Thank you for watching. Now, let's go. The evolution of quantum computers didn't just magically appear as a tech miracle. In reality, they are the culmination of a long and challenging journey, driven by the need to compute and simulate complex systems going back centuries. When scientists realized that classical computers had hit a wall in simulating quantum phenomena, that's when the seed of quantum computing began to sprout. To truly appreciate the development of this groundbreaking technology, let's hop into our time machine and travel through three key phases, witnessing humanity's remarkable strides in the quantum realm. Phase 1. The emergence of analog computers, early 20th century. Let's turn back the clock to ancient times, when the world's oldest analog computer, the Antikythera mechanism, made its debut. In 1901, Greek divers accidentally discovered this remarkable device in a shipwreck near the small island of Antikythera, just north of Crete. The Antikythera mechanism was, in fact, an incredibly complex system of mechanical gears designed to predict astronomical events like the lunar cycle, solar eclipses, and planetary movements. With the help of 3D X-ray scanning technology, scientists unraveled its intricate workings and discovered that ancient Greeks possessed astonishing mathematical and astronomical knowledge. Although it was just a set of mechanical gears, the Antikythera mechanism is the grandfather of modern computers, marking the first chapter in humanity's quest for computational technology. Phase 2. The digital computing era, 1940s to present. As society advanced, the demand for precise and efficient calculations became increasingly critical. From simple counting tools like tally sticks and animal bones, humanity transitioned into the era of mechanical and digital computing. Charles Babbage, often hailed as the father of computing, pioneered the first programmable mechanical computer. This machine, powered by hundreds of gears, levers, and pulleys, was capable of performing complex calculations, revolutionizing fields such as banking, commerce, and maritime navigation. Milestones of digital computer generations. First generation, 1940 to 1956. The UNIVAC I, the first commercial computer, made history by accurately predicting the outcome of the U.S. presidential election, proving the power of computing to the world.
Which we have borrowed to help us predict this election. Basis of the returns that we've had so far. Now back to Walter Cronkite.
Second generation, 1956 to 1963. The invention of the transistor made computers smaller, more efficient, and more reliable, paving the way for modern computing. Third generation, 1964 to 1971. The introduction of integrated circuits, ICs, enabled computers like the IBM system /360 to support multitasking, meeting the growing demands of businesses and organizations. Fourth generation, 1971 to present. The birth of the microprocessor, starting with the Intel 4004, ignited the personal computer, PC revolution, leading to the rise of iconic operating systems like Microsoft Windows and Apple Mac OS. Phase 3, the quantum computing era, the future. As digital computers approach their physical limits, scientists began envisioning an entirely new kind of machine, one that could harness the quantum properties of atomic particles to perform calculations at unprecedented speeds. The brilliant physicist Richard Feynman posed a revolutionary question. Can we shrink transistors down to the size of an atom? He realized that by leveraging bizarre quantum phenomena like superposition and quantum entanglement, we could build computers far beyond anything seen before. This groundbreaking idea paved the way for the birth of quantum computing. Key milestones in the quest for quantum computing. 1980. Paul Benioff proposed the idea of using quantum mechanics for computation, laying the groundwork for deeper research. 1981. Richard Feynman and Yuri Manin discovered that classical computers struggled to efficiently simulate quantum systems, highlighting the need for a new computing paradigm. 1994. Peter Shor developed Shor's algorithm, enabling quantum computers to factor large prime numbers exponentially faster, posing a major threat to traditional encryption systems like RSA. 2019. Google shocked the world by claiming quantum supremacy with its Sycamore processor, 54 qubits, solving a problem in 200 seconds that would take the world's most powerful supercomputer 10,000 years to complete. 2020, present. Tech giants like IBM, Google, and D-Wave have been racing to advance quantum computing with potential applications in chemistry, finance, AI, and logistics. 2023, IBM introduced IBM Eagle with 127 qubits, marking a major leap in scalability and real-world applications of quantum computers. With these rapid advancements, quantum computing is set to revolutionize not just the way we calculate, but also how we understand and shape the world around us. Up next, we'll dive deeper into the core principles of quantum computing and explore its game-changing applications across various industries. But before we venture further into this mind-bending quantum realm, let's take a quick recap of the classical computers we still use every day. Classical computers. Classical computers, including today's most powerful supercomputers, operate on the binary system BT. This means that all data is represented using just two fundamental states, 0 and 1. Each individual value is called a bit. To simplify, imagine a light switch. It can only be on or off, with no in-between states. This straightforward binary logic is the foundation of all classical computing. How classical computers process data. Classical computers process information sequentially, meaning they execute tasks step by step. For example, if you need to test 1,000 passwords to unlock an account, a classical computer would check them one by one, from the first to the last, until it finds the correct one. Classical computers rely on billions of transistors embedded in microprocessors, commonly referred to as CPUs, to handle data. Modern processors contain anywhere from billions to hundreds of billions of transistors, working together to perform millions, or even billions, of calculations per second. When you link thousands of CPUs together, you get supercomputers capable of solving the most complex problems, such as weather forecasting, nuclear reaction simulations, calculating planetary orbits in the solar system. Power and limitations of classical computers. Classical computers are extremely powerful when handling linear calculations or tasks that require precise, step-by-step execution. When additional computing power is needed, supercomputers combine multiple CPUs to process tasks in parallel. However, no matter how advanced they become, classical computers still follow a sequential approach, breaking problems into smaller parts and solving them one by one. Key limitations: speed constraints. For problems with astronomical possibilities, classical computers require exponentially increasing time to explore all potential solutions. Physical limitations. Increasing computational power relies on adding more CPUs or transistors, which introduces challenges like size constraints, energy consumption, heat dissipation. Not optimized for quantum problems. Some advanced problems, like quantum physics simulations, molecular chemistry, and AI optimizations, require simultaneous evaluation of millions of possibilities, something classical computers struggle to achieve efficiently. This is where quantum computing takes over. Instead of tackling problems step by step, quantum computers process multiple possibilities at the same time, unlocking unprecedented computational power. Quantum computers. Imagine you're navigating a gigantic maze. A classical computer, even the most powerful supercomputer, would explore one path at a time, testing each possibility sequentially until it finds the exit. A quantum computer, however, can explore all possible paths simultaneously, allowing it to find the solution exponentially faster. Key differences between quantum and classical computers. Quantum computers redefine computing by replacing traditional bits with qubits, unlocking unprecedented processing power. Bit. Classical computer can only be 0 or 1 at a time. Similar to a light switch, either on, 1, or off, 0. Qubit, quantum computer, can be 0, 1, or both at the same time, thanks to quantum superposition. Like a magic light switch that is both on and off at the same time. This means quantum computers don't just compute faster, they compute differently, making them game changers for cryptography, AI, drug discovery, and more. The power of qubits. Imagine this. An 8-bit classical computer can only represent 1 out of 256 possible values at any given moment. But an 8-qubit quantum computer, it holds all 256 values simultaneously. This insane ability to process multiple possibilities at once is what gives quantum computers their mind-blowing parallel computing power. What is quantum mechanics? Quantum mechanics is the branch of physics that studies the bizarre behavior of matter and energy at an ultra-microscopic scale. Think atoms and subatomic particles like electrons, photons, and neutrons. Developed in the early 20th century, it explains the strange phenomena that classical physics just couldn't figure out, like the dual nature of light and the unpredictable antics of fundamental particles. For example, if you zoom in on a beam of light, you'll find that its quantum unit is a photon. If you break apart an atom, its quantum components are electrons, protons, and neutrons. To grasp the mind-bending nature of a qubit, let's take inspiration from the famous coin flip experiment by David Deutsch and Richard Jazza. In the classical world, if you flip a coin, it lands on heads or tails. Simple, right? But in the quantum world, the coin is in a state of both heads and tails at the same time, until you actually observe it. This strange duality is possible thanks to two game-changing principles of quantum physics. Quantum superposition. If a classical bit is like a coin that can only be heads or tails, then a qubit is like a spinning coin, existing in both heads and tails at the same time. Or, imagine a musical instrument that can play all notes simultaneously instead of just one at a time. This unique ability allows qubit to store and process multiple values simultaneously, unlocking unparalleled parallel computing power. To truly grasp quantum superposition, let's look at one of the most mind-bending thought experiments ever created, Schrödinger's cat. Imagine a completely sealed box that no one can see inside. Inside the box, we have a radioactive atom with a 50% chance of decaying within an hour, a vial of poison connected to a hammer mechanism. How it works. If the atom decays, the hammer breaks the vial, releasing poison, and, well, goodbye, kitty. If the atom doesn't decay, the cat stays safe and sound inside the box. But here's where it gets wild. Quantum superposition. The cat is both alive and dead. Before you open the box, quantum mechanics tells us that the atom is both decayed and not decayed at the same time. And since the cat's fate is entangled with the atom, it is also in a superposition of being both alive and dead simultaneously. When does the cat's fate get decided? The moment someone opens the box and observes it. In quantum mechanics, this active measurement forces the system to collapse into a single, definite state. Either the cat is alive or it is dead. Beyond just alive or dead, the true power of quantum superposition. In reality, a quantum system isn't limited to just two simple states. The cat could be both alive and dead, both playing and jumping, both lying still and feeling unwell, or any other imaginable state in between. This highlights the mind-blowing potential of quantum superposition, where a system can exist in countless states simultaneously. And that's exactly why quantum computers can process an astronomical number of possibilities at once, paving the way for revolutionary breakthroughs in computing. Why is this experiment so important for quantum computing? Because it beautifully illustrates the hidden power and unmatched processing capabilities of quantum computers, all thanks to the mind-bending principles of quantum mechanics. Demonstrates quantum computing power. The Schrödinger's cat thought experiment helps visualize how quantum computers can perform multiple calculations in parallel. Supercharges computation speed. Unlike classical computers that brute force solutions one by one, quantum computers explore many possibilities simultaneously. The role of the observer highlights how measurement determines the outcome, just like how a quantum computer picks its final answer only when needed. Quantum computers in action. If each qubit is like Schrödinger's cat, then having millions of qubits in superposition means quantum computers can process enormous amounts of data at once. Real-world analogy. A classical computer is like someone opening each box one by one to find the living cat. A quantum computer is like opening all the boxes at the same time and instantly knowing which one contains the living cat. Quantum entanglement. When qubits become quantum entangled, their states become inseparably linked, no matter how far apart they are. This is one of the most mind-blowing and mysterious phenomena in quantum physics. Simply put, when one qubit changes its state, the others instantly adjust, even if they're light years apart. This ultra-fast connection allows quantum computers to solve complex problems at speeds never seen before. Think of it like this. Imagine you and your best friend can instantly sense each other's emotions, even if you're thousands of miles away. That's quantum entanglement. When two qubits are entangled, Changing one qubit's state immediately affects the other, no matter the distance. It's as if an invisible, ultra-powerful force connects them across space. A fun example. Imagine you have two gloves, one right-handed and one left-handed. If you find one glove, you instantly know the other must be its opposite, no matter where it is. That's how qubits in a quantum computer stay linked. Quantum computers harness entanglement to exchange information and compute at lightning speed, making them exponentially more powerful than classical computers. Albert Einstein once called quantum entanglement a spooky action at a distance because it defies classical physics. According to traditional physics, nothing can travel faster than light. But entanglement seems to break this rule. And it's not just science fiction. Scientists have conducted numerous experiments to test quantum entanglement, and after decades of research, they have definitively proven that it is real. In 2022, the Nobel Prize in Physics was awarded to scientists who definitively confirmed that there are no loopholes in quantum entanglement experiments. Their groundbreaking work proved that this bizarre phenomenon cannot be explained by classical physics, further solidifying the mind-bending reality of the quantum world. With quantum entanglement, quantum computers can achieve mind-blowing speeds, unlocking new frontiers in quantum cryptography, molecular simulation, artificial intelligence. But there's a catch. The quantum world isn't just magical, it's also insanely difficult to control. Manipulating qubits is extremely complex, and scientists are still figuring out how to fully harness this power. In the quantum realm, where things are smaller than atoms, the rules of classical physics no longer apply. Quantum entanglement isn't just a fascinating scientific curiosity, it's the key to future technology. From hypersecure encryption to breakthrough AI, we're on the verge of a technological revolution once thought possible only in sci-fi movies. Whoa, that was quite a deep dive into quantum computing, wasn't it? Today, we've unlocked the fundamentals, explored the mind-bending world of qubits, and even tackled some of the craziest quantum principles. But don't go anywhere just yet. This journey is just getting started. In the next video, we'll uncover why quantum computers are actually necessary and reveal their insanely powerful real-world applications. And of course, the million-dollar question, will quantum computers steal our jobs, just like AI? Or, who knows, maybe they'll be too busy playing video games with AI instead. To make sure you don't miss out on these mind-blowing discoveries, hit that subscribe button and turn on the notification bell right now. Today's video ends here. Don't hesitate to leave a comment below to let me know if you liked this video. Please share the love and give it a thumb up, as well as hit the subscribe button so you never miss an update from us. Thanks for watching and see you soon. Bye-bye.